Okay, so here we have a function of x, and it's equal to 3x plus 2 all squared. And if we were to find the derivative of this function, first we'd have to expand these brackets out. So we can rewrite that as 3x plus 2 times 3x plus 2. Expand out the brackets to get 9x squared plus 12x plus 4. And we can now find the derivative because all of our terms are in that nice ax to the power of n form. So we end up with 18x plus 12 as our derivative. However, what if we had this function g of x over here, which was equal to 3x plus 2, and in this time it's to the power of a greater power, so to say to the power of 7. Well, we're going to have to write out and expand 7 brackets before we can take the derivative, okay? And that's going to take a lot of time and a lot of work. So the quicker way that we can do this is using what we call the chain rule. And the chain rule for differentiation deals with a function inside of a function. So remember, the product rule dealt with functions being multiplied together, and the quotient rule dealt with finding the derivatives of functions that were being divided by each other. But the chain rule deals with the combination of functions, or a function inside of a function. So the chain rule says that if y is equal to some function of u, where u is actually a function of x, okay, then the derivative of y with respect to x at dy dx, which is what we'll be looking to find, is equal to dy du times by du dx. Okay, so this dy du is taking the derivative of this part here. And this du dx is taking the derivative of this part here. And we're multiplying those together. So this will make a little bit more sense if we do an example. So let's have an example. And our example, let's say that y is equal to 3x plus 2 all to the power of 7. So what we had with our function up the top there just before. Well, we need to rewrite this 3x plus 2 to the power of 7 as a function of u, where u is actually a function of x. So if I said that this was equal to u to the power of 7, where u is equal to 3x plus 2, let's rewrite that, 3x plus 2, then we have f of u being our u to the power of 7, and our g of x is equal to 3x plus 2. So if we find our two separate derivatives, so in this case dy du is going to be 7u to the power of 6, and our du dx is going to be equal to 3, then we just have to multiply these together. So if we multiply these terms together, or highlight them in purple, these here, we just end up with 21u to the power of 6. But we need to substitute what u is back in terms of x. Well, we know that u is equal to 3x plus 2. So we end up with 21 lots of 3x plus 2 all to the power of 6. Okay, and that's our derivative. So what we've done is we've rewritten this function here in terms of a function of u. So in this case, we've let it be u to the power of 7. But u is in this case equal to 3x plus 2. So anything inside the brackets we've just written as u, and we've made a substitution there. Okay, we then found that the separate derivatives and multiply them together. And if we look at the relationship between this original function and this derivative, well, what we're doing is we're treating this as if we could just take it as 7 lots of 3x plus 2 to the power of 6, but then we just have to multiply by the derivative of what's inside the brackets. So multiplying by that 3 there. So let's do another example and see if we can sort of start to get the hang of it. So I want to keep this part here for us to be able to refer to. So I'm going to bring that down there. And we're going to do another example. And I'll just highlight these again. Whoop. Where are we going? Let's highlight this yellow and this part here blue. Okay, and let's do another example. So for example, we have y is equal to, let's say, 7x plus 4 all to the power of 3. So 7x plus 4 cubed. And we're now asked to find dy dx. Well, we can rewrite this as u to the power of 3, where u is equal to 7x plus 4. Okay? Well, now dy over du is equal to 3u squared. and du dx is equal to 7. So if we multiply these terms together, we end up with 21u squared, and substituting u is equal to 7x plus 4 back into this 21u squared, we end up with 21 lots of 7x plus 4 all squared. And looking at the relationship between this original function and this derivative again, what we've done is we've pretended that we can sort of just take this as 3 lots of 7x plus 4 all squared, but we just have to remember to multiply by the derivative of what's inside the bracket. So in this case, the derivative of what's inside, or the derivative of our u, is actually equal to 7. Okay, so we multiply this function by 7, we end up with 21 lots of 7x plus 4 squared, which is our final answer. Okay, so hopefully that's making a little bit of sense about how that chain rule works. But what I'd like to do now is take a closer look and look at how this links into the trigonometry that we've been learning with our derivatives of sine and cosine. So I want to show why. Remember that the derivative of, say, sine of x is equal to sine of some function of x. Sorry, let's say the derivative of sine of some function of x was equal to the derivative of that function times by cosine of function of x. And we want to see why this derivative part comes out in this equation. So let's use a chain rule to prove that. So for example, we are asked to find the derivative. So find the derivative with respect to x of sine of, say, 3x squared. Well, we can rewrite this function as sine of u, where u is equal to 3x squared. Well, now, if y was equal to sine of 3x, so y is equal to sine of 3x squared, that's just the function, okay? Then dy over du, we know that the derivative of sine is cosine. And we proved that on the couple of videos back on our derivative graphs. Okay, so we know that dy du is just cosine of u. But du dx is equal to the derivative of what's inside here. Okay, that's going to be 6x. So if we multiply these terms together, we get 6x times the cosine of u. And we know that u is equal to 3x squared. So we get 6x times the cosine of 3x squared. So that's where this part comes into play in our formula for the derivatives of sine and cosine, having to take that derivative and multiply it by just the cosine or the sine of the original function. That comes down to the chain rule. So here, in our example, we took the derivative of sine of 3 of x squared, and we just worked out that that was cosine of 3 of x squared, but we have to multiply by the derivative of what's inside our brackets there. Okay, so that's all down to the chain rule. So I just want to look at one more example, which is if we're dealing with to the power of halves, okay, or fractions, okay. It's the exact same thing, it's just a little bit more to think about. So let's cut and paste this again. So we'll take our chain rule, which is there, and we're going to bring it down to here. Oh, it didn't carry that highlight in yellow, but that's all good. What's it doing? There we go. Let's highlight that. And let's deal with the example of y is equal to 3x plus 2 to the power of a half, for example. So to the power of fractions. Well, once again, we just say that this is equal to u to the power of a half, where u is equal to 3x plus 2. Okay? Well, if we take the derivative of y with respect to u, we end up with a half of u to the power of negative a half. Okay, and if we take the derivative of u with respect to x, so du over dx, well, that's equal to just 3 again. That's that part there. Okay, so we can rewrite this half of u to the power of a negative a half. Okay, so if we multiply these terms together, we end up with 3 over 2 times by u to the power of negative a half. But u to the power of negative a half is just 1 over u to the power of a half, right? So this becomes 3 over 2u to the power of positive a half. Well, that u to the power of a half can be written as the square root of u. Okay, so we can rewrite that as the square root of u. But remembering that u is equal to 3x plus 2, we can substitute that back in and we get 3 over 2 times the square root of 3x plus 2. Okay? So that's pretty much it for the chain rule. Okay, so we've had a look at what the chain rule is and how it's useful, because if we have to deal with, like over here, this 3x plus 2 to the power of 7, or to a large power, it's hard to expand out that many brackets. And then we just had a look at where this derivative of x part comes into play with our add derivative of sine and cosine rules, and then just a few other examples. Okay, so that's it for the chain rule.